The main purpose of this lab is to visualize the relationship between distance and magnetic field using a bar magnet in a smartphone. We're going to also create a computational model to calculate the magnetic field and determine the distance dependence of a bar magnet using the Biot-Savart law and experimental methods. We can use this distance dependence to find the magnetic moment. For a preview of the results, the calculated magnetic dipole was 1.72 amperes by meter squared. The experimental value of the magnetic field was 6.02 e to the negative 5 teslas, and the computational value is 2.17 e to the negative 5 teslas. The two main concepts in this experiment that we're going to be using is the Biot-Savart law, which can be used to find the magnetic field from a current-emitting element. So in this experiment, it's going to be our bar magnet, and also the distance dependence, which is a relationship that allows us to compare how distance affects the magnitude of the magnetic field. The system for our procedure is going to be the bar magnet, and the surroundings is going to be everything else, including Earth. We're also going to assume that the bar magnet acts as a magnetic dipole. We're going to want to make sure that we're setting up our phone and magnet so that we're only measuring the magnetic field from the magnet and not from Earth. We're going to conduct the procedure so that the phone is aligned with the north-south axis of the Earth and that the bar magnet is aligned to the east-west axis so that the magnet's on-axis field is orthogonal to the Earth's magnetic field. This will allow us to only have to measure the X component from the magnet using our app. Next, to find the location of our magnometer, we're going to slide the phone as the blue arrow shows on the right to find the position where the magnitude of the X component is the largest and the Y component is the smallest. We're going to mark this location with tape and then rotate the phone 90 degrees to the right and find the position where the Y component is the largest and the X component is the smallest, and mark that point as well. Where the top two edges of the tape intersect is where our magnometer lies. Now that we have the location of our magnometer, there are certain values that we want to see the distance at which that value shows up on our app for the X component of the magnetic field. These are 20, 70, 120, 170, and 220 Tesla. We've gone ahead and done 3 trials for each value, documented the distance and the magnetic field shown on the phone. From this, we're able to create a relationship which gives us the equation that we can use to calculate the distance dependence. You also want to take off-axis measurements, where you're going to set the magnometer a certain equal x and y distance away from the bar magnet and measure the x, y, and z components of the magnetic field. You're also going to have to adjust the y component using the y component of the magnetic field due to Earth at your location. This will give us a net magnetic field that we have to be 6.2 e to the negative 5 Tesla. We can use our line of best fit from our graph to find n and the value of k. N is going to be negative 3.1709, which is the slope of the equation. We can also set L and K equal to the y-intercept, negative 14.878, and find the value of K, which is 3.45 e to the negative 7. We're going to want to isolate mu from our equation and plug in the values that we have in order to find the magnetic dipole moment, which is going to be equal to 1.72 amperes times meter squared. 2 observations that we made during the experiment is first, as the magnometer gets farther away from the magnet, it measures a near zero magnetic field in the X direction. In contrary, as the magnometer moves closer to the magnet, the measured X component of the magnetic field increases. Starting from the top left, we can see that we inputted the magnetic moment that we calculated previously from the experiment, and then created a function that calculates the magnetic field using the Biot-Savart law. Then at the top right, we can see where we create 2 arrows to calculate the on-axis magnetic field and 4 for the perpendicular magnetic field. And then we're going to insert our average d perp value that we also found from our experiment. Then at the bottom right, we can see where we create an arrow to represent the magnetic field 45 degrees from the axis. So in our model created from our code, we have the 2 green arrows showing the on-axis field and the 4 blue arrows showing the off-axis. We also have the 1 orange arrow showing the one at 45 degrees, and the calculated magnitude here is going to be 2.179 e to the negative 5 Tesla. And to compare that to our experimental value, which was 6.02 e to the negative 5 Tesla, there's definitely a significant difference between these values. So if we did not properly orient our experiment to compensate for magnetic north, it would make it so our measurement taken is also including the Earth's magnetic field, and this would offset our result. If we were to stick 2 identical magnets together and run the experiment again, The values would increase, possibly double in value, but cannot be guaranteed, but the direction of the field will stay the same. The reason why our computational experimental values do not match up is because the computational model does not take into account outside forces such as the Earth's magnetic field. We tried our best to make sure that we're not accounting for the Earth, but there's still possibility for human error, such as not properly aligning the phone so it's exactly orthogonal to the Earth's magnetic field, as well as not properly identifying the exact location of the magnometer, which can also affect our results.